Welcome to our lesson on acids, bases, and pH. Our objectives for today, we're going to talk about some of the characteristics of acids and bases and describe the dissociation of acids and bases and also the dissociation of water. We're going to state some examples of acid-base indicators, define this super cool math thing, logarithms. We're going to calculate some pH and some pOH. Because of those logarithms, those calculations, highly recommend that you have a calculator nearby. We're also going to need some molar masses and some formulae, so grab your periodic tables. Let's talk first about some characteristics of acids and bases. Acids tend to taste sour. They're electrolytic. That means that they can conduct electricity as a solution, and they can do that because they have ions, charged particles floating around in the solutions. One of the ions in acids are hydrogen ions, or H pluses, and the pH of acids are less than 7. Some examples of acids: vinegar, which is also known as acetic acid or ethanoic acid; lemon juice, which contains citric acid; and ascorbic acid, stomach acid, which is hydrochloric acid. And then carbonated drinks. The carbonation comes from CO2 molecules, gas bubbles in the sodas. When those combine with water, we sometimes get carbonic acid. Bases are a little bit different. Sometimes we use, instead of basic, we can say alkaline. Alkaline and basic mean the same thing. Instead of tasting sour, they taste bitter, but they are also electrolytic. They can also conduct electricity because they also have ions. But for most, not all, but for most of our bases, they're going to produce hydroxide polyatomic ions. That's one of the ions that makes it electrolytic. Their pHs are going to be greater than 7. Remember that acids were less than 7. Bases will be greater than 7. Household cleaners like Windex are often basic because they have ammonia as one of their ingredients, and acid tablets like Rolaids or Tums are also basic. Blood is just a little bit basic, and then baking soda is a little bit basic. This lovely diagram is showing us some examples of acids and bases on this pH scale. So here in the middle we have 7. A pH of 7 is considered neutral. Water has a pH of 7. If we have pHs that are greater than 7, we have bases. Bases are examples of solutions that have pHs that are greater than 7. And interestingly, the further away from 7 we get, the stronger, the more concentrated the base. So something that's a pH of 8, not super concentrated, not super strong base, but 14, oh my gosh, melt your face off. Drain cleaner is a strong concentrated base. Sodium hydroxide is the most common compound in drain cleaners, and it's quite reactive, which is why it's such a good drain cleaner. On the opposite side, we have our acids. And again, the further away from 7 we get, the stronger, the more concentrated the acids. Acids have pHs less than 7. Something like milk is just a tiny little bit acidic, not very far away from water. Hydrochloric acid way down here is strong and concentrated with that pH of 0. So this diagram is showing us just 0 to 14. We can actually have pHs that are negative. We can have pHs greater than 14. It's just not super common in nature. Those tend to be very reactive things that wouldn't exist. They would react and not be quite so strong. But in the labs, we certainly can make solutions, keep them separate from the environment, that have pHs that are negative, pHs that are greater than 14. So go ahead and take a moment, practice that information that you just learned, and decide if each of these characteristics is describing an acid or a base, or perhaps even both. Hopefully you decided that. Bitter are bases. Acids taste sour. pH of less than 7 is an acid. pH of greater than 7 is a base. Electrolyte, that's both. Acids and bases. Can conduct electricity in a solution. That's the same thing as being an electrolyte, so it's going to be, once again, both acids and bases. What produces hydroxide ions? That's going to be a base. Hydrogen ions are acids. Orange juice is an example of an acid, and ammonia is an example of a base. Acids and bases both dissociate or break up when they are dissolved in water. They're not associated with the whole entire molecules. And so both acids and bases can dissociate. And interestingly, the more dissociation there is, the stronger the acid or the base. And then because we have more ions in the solution, it also becomes a stronger electrolyte. So this lovely diagram is kind of showing us the dissociation of a strong acid and a weaker acid. Here, notice that these acid molecules, that whole acid molecule is that hydrogen ion, we can also call it a proton, and then that negative ion, whatever is left over when the proton pops off. If we're talking about hydrochloric acid, which is a strong acid, then that chloride ion would be that negative ion. In the solution, in the water, notice that all of these guys are breaking apart. The protons, the hydrogen ions, are separate from all of those chloride ions. So we have lots and lots of ions, which is why it's such a good and strong electrolyte. This weak acid, and this is maybe acetic acid is going to pop apart into an H plus and then an acetate polyatomic ion, that's C2H3O. Sorry, O2, and what happens here is most of these guys are actually staying stuck together. So instead of all of those acid molecules popping apart into H pluses and acetate ions, we have just a few of them are popping apart, lots of them are staying stuck together. And so this is a weaker acid, it doesn't dissociate quite as much. Because there are fewer ions, it is not as strong of an electrolyte. So acids are going to dissociate to form those hydrogen ions and an anion. For example, with hydrochloric acid, it would be chloride. The hydrogen ion can also be considered a proton, and so sometimes we're going to call acids proton donors because they give away their protons, their hydrogen ions. Interestingly, those hydrogen ions will often combine with water. That hydrogen ion will combine with water to form this thing called hydronium H3O+. Because that hydrogen ion, that proton has a positive charge, it's attracted to the negative electrons that are not in bonds on the water, the oxygen side of the water. They'll just kind of stick together. Here's that hydrogen ion stuck to the water molecule. Because it has an extra proton, it is now a positive charge, and we're going to call it hydronium. H3O+ is hydronium. And we're going to talk in a couple of slides about how we can look at the concentration of the hydronium ion, this guy, how much of that there is in a solution, and that will help us calculate pH. Many bases will also dissociate, not all of them, there are some exceptions. So we're going to go with many bases. Many bases also dissociate and form hydroxide polyatomic ions and then some cation. Sodium hydroxide, which is one of those ingredients in most of our drain cleaners, is going to dissociate into that hydroxide polyatomic ion and then a sodium cation. Often those hydroxide polyatomic ions are going to combine with a hydrogen ion, and that's going to make water. And so we're going to call our bases proton acceptors because they're accepting the hydrogen ion to make that water molecule. Remember that hydroxide polyatomic ion OH- is on our list of polyatomic ions. And what's super cool is we have this thing called POH in addition to pH. pH we talk a lot about in the common world. In chemistry, equally important is POH. pH is based on the concentration of the hydrogen ion. POH is based on the concentration of the hydroxide polyatomic ion. Super cool thing about water. So water is also constantly dissociating and then reassociating. So it'll pop apart and then pop back together, pop apart and pop back together. It pops apart to release hydrogen ions. It's going to let that hydrogen ion pop off. What's left over is this hydroxide polyatomic ion. Because it is giving away a hydrogen ion, it is considered an acid. It's a proton donor. But here's what's crazy cool. Other water molecules that are sitting next to this water molecule, this guy right here, because he has those non-bonding pairs of electrons on the oxygen side of the molecule. This positively charged hydrogen ion is going to be attracted to those electrons, and it sticks together to form hydronium. This guy is accepting that proton. That makes it a base. Water is both a base and an acid. Crazy sauce. We have vocabulary to describe that. So water is what we call amphiprotic and amphoteric. These mean almost the same thing. This is focusing more on how it can be both a proton donor and a proton acceptor. This is saying that it can act like an acid and a base, which is pretty similar to being a proton acceptor or proton donor. Water can be both an acid or a base because it can produce hydrogen ions and also hydroxide ions. The hydrogen ion that was here pops onto that guy to make our hydronium ion. So super quick review, tell me, what do acids dissociate to produce? What do bases dissociate to produce? Why do we call water amphoteric? Acids dissociate to produce hydrogen ions. Many of our bases dissociate to produce hydroxide polyatomic ions. Water is described as amphoteric because we can take water and break it apart into a hydrogen ion, which makes it an acid, and a hydroxide ion, which makes it a base. So crazy cool. So we have some substances that are called acid-base indicators, and they allow us to know if a chemical is an acid or a base by some kind of fun color change. So these are just a few of the many acid-base indicators that exist. Phenolphthalein we will use in our titration lab in a couple days. Phenolphthalein is colorless in an acid and turns this lovely bright pink in a base. Bromothymol blue is yellow in an acid, blue in a base. Purple cabbage juice. Literally, you buy purple cabbage, sometimes called red cabbage, at the grocery store, and you boil it in some water. And then you take that water, the juice from the cabbage, and it'll turn pink if you add an acid and green if you add it to a base. pH paper is super helpful because it doesn't just say acid or base, it actually gives a range of colors for different pH values. So here is an example of a key for some pH paper. Notice that we have different colors for lots of acidic pHs and for lots of different basic pHs as well. We've been talking a lot about pH. Let's actually figure out what even is this thing we call pH. So the guy who invented pH, he never told anybody exactly what it means, but we think it's probably either the power or the potential of hydronium or that hydrogen ion concentration. So P for power, H for hydronium or hydrogen. We're going to calculate it by finding the exponent or the power on a 10. So 10 to what power is equal to the concentration of the hydronium ion concentration, the hydrogen concentration. That's the pH. For example, if I have a hydronium or a hydrogen ion concentration of 1 times 10 to the minus 3 molar. I'm not going to worry about the 1 because 1 times anything doesn't change anything. So I have 10 to the power of negative 3. I'm going to take the negative exponent. The exponent is negative 3. So negative 3 is positive 3. The negative exponent on the 10 is the pH. The pH is equal to 3 because I take the negative 3. That's the exponent on the 10. This kind of math is known as a logarithm. Logarithms are the maths of finding exponents. For example, if I have a, this base to some power x, and I find this number y, a raised to the x power is equal to some number y. Then when I'm using logarithms, I'm trying to figure out what even is that exponent. So if I have a base of a, and when I raise it to an exponent, it's equal to y, that exponent is what I'm trying to find. For example, log base 10 of 1,000 is asking me to figure out, this is my base of 10, what exponent on a 10 is going to give me 1,000? 10 to what power is equal to 1,000? Well, I know that 10 to the third power, 10 times 10 times 10, 3 tens gives me 1,000. So log base 10 of 1,000 is equal to 3 because 10 raised to the third power is equal to 1,000. How about log base 3 of 9? 3, that's my base, to what power is equal to 9? 3 to what power is equal to 9? Base of 3, number 9, that exponent is going to be a 2. I know that 3 squared is equal to 9, so log base 3 of 9 is equal to 2. How about one more? Log base 5 of 5. This is asking me to figure out 5 to what power is equal to 5? My base of 5, my number 5, what's going to be that power? 5 to what power is equal to 5? We know that's a 1. So log base 5 of 5 is equal to 1. You try these ones. Answers are 2, because we know that 10 squared is equal to 100, and so that exponent is a 2. 3 to what power is equal to 27? We know that 3 cubed is equal to 27, so our answer is 3, because 3 to the third power gives us 27. Log base 2 of 32, oh my gosh, that's 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. How many 2's is that? That's 5 2's. My answer is 5. 2 to the fifth power is equal to 32. So pH. pH is a logarithm. What we're going to do, and our formula is given to us on our formula chart, we're going to find the negative logarithm of the hydrogen ion concentration. I'm going to figure out the hydrogen ion concentration, and sometimes we use those brackets as braces. I think these are braces or brackets. I can never remember. Anyhow, so we use this as a shortcut to talk about concentration. So I'm going to figure out what's the concentration in some molarity. So what's my molarity? My molar of the hydrogen ion concentration. I'm going to put that in a 10 to some power. I'm going to take that power, I'm going to make it negative, and that's my pH. So pH is the exponent on a 10, and I'm going to flip this sign from negative to positive or positive to negative, and that's it. You may notice that there's not a base in here. You're like, wait, log to what base? If there's no base given on your logarithm, we call that a common log, and it's going to be base 10. So if there's no base written, you're going to assume that it must be base 10. It's the common log. So if I have a hydrogen ion concentration of 1 times 10 to the minus 8, I don't have to worry about that 1 times, because 1 times anything doesn't change a thing. So I already have my 10 to a power. I'm going to grab that power, I'm going to make it negative. Negative 8. Negative 8 is positive 8. My pH is 8. Sometimes our hydrogen ion concentrations are given to us as 10 to some power. Then it's super easy to figure out what's the power on the 10. But sometimes our hydrogen ion concentrations are given to us in something like 0.00023. I don't know what that is equal to as 10 to some power. And so we need to use our calculators to find some of our logarithms. How are we going to do this? Log button is here. So remember that pH is the negative log. So we do want to start with that negative button, which is here. Don't use the minus sign. Make sure you use the negative sign. So we're going to do negative log, and then we're going to should have an automatic parentheses, open parentheses, propagate. But just in case you can push that button, it's here. You're going to type in your number, your hydrogen ion concentration. In this instance, I've got 0.00023. Do closed parentheses and then enter, and you'll have your pH, negative log of that hydrogen ion concentration. If you had something in scientific notation instead, 2.3 times 10 to the 1, 2, 3, 4, 5, 10 to the minus 5. If the molarity was given to us in scientific notation instead, we can do the same thing. pH is going to be the negative, push the negative button, log, push the log button, and then type in that concentration. You have a couple choices. You can do 2.3, 2.3, and then you can do times 10. Use your caret button, raise to the negative 5, close parentheses, and enter. Your other option is negative. Use your negative log button. Parentheses should automatically propagate, and then you can type in 2.3. And instead of doing times 1, 0, caret negative 5, what you can do instead is that second function, and then on top of the comma here is an EE. That E button is telling the calculator that we are working in scientific notation. An E will pop up on your screen. Type in your exponent, negative 5, close parentheses, enter, and you should have your logarithm. Let's practice. So use your calculator or your brain to find the pH, the negative common log of these following hydrogen ion concentrations. So if you have a hydrogen ion concentration of 1 times 10 to the minus 2, I don't need my calculator for this one because this is a 1, which means that it doesn't change anything. So I just have to find the negative exponent on the 10. The exponent on the 10 is negative 2. So negative 2 gives me a pH of 2. Hydrogen ion concentration 1 times 10 to the minus 4. Because this is 1, it doesn't change anything. I just need to look at 10 to the minus 4. I want to find the exponent on the 10. It's negative 4. because my pH is a negative log, I'm going to make it negative 4. The pH is going to be equal to 4. These guys, I'm going to need my calculator because that's not a 1, and so it's not quite as easy as just looking at the exponent. So on my calculator, I'm going to type negative log. I'm going to type in 3.4, and I like to use the second function EE. So I'm going to do second function EE button, and I'm going to type in that -6 exponent and enter, and my pH is going to be equal to 5.4685, lots of digits. Sig figs on logarithms are kind of weird. So I'm going to count the number of sig figs that I have in my original data, and that's the number of decimal places in the logarithm that I get to keep. So since I have 2 sig figs in my data, I'm going to keep 2 decimal places. That 8 is going to make that 6 a 7. My final pH is 5.47. 5.47 is the pH of that solution. Let's do one more together, and then I'm going to have you do some on your own. So we're going to do negative log of 1.9 times 10 to the -12th power. Negative log of 1.9 times 10 to the -12th power gives us 11.72124. So many digits. We're going to keep 2 decimal places because I have 2 sig figs here. Keep 2 decimal places here. That 1 doesn't do anything to that 2. And so my final answer is 11.72. That's the pH. Good. Do these ones on your own. Answers. For these first 2, you don't need to use your calculator because it's 1. You can ignore that. The exponent is a -3, so -3 means that the pH is equal to 3. Here, -8, the pH is going to be equal to 8. These ones we do need to use a calculator, so negative log of 2.4 times 10 to the -12 gives you a pH of 11.62 when we check our sig figs. Negative log of 6.9 times 10 to the -1 is going to give us a pH of, this one's kind of quirky, 0.16. Good? All right. So in chemistry, we have not just pH, but we also have this pOH. And the formula is not given to you on your formula chart, but it's the same as finding the pH. But instead of using the hydrogen ion concentration, we're going to use the hydroxide concentration. So if the hydroxide concentration is 1 times 10 to the -8, I'm going to find the negative log of the hydroxide concentration. Negative log of 10 to the -8, the pOH will be equal to 8. So it's just like pH, but we're looking at hydroxide instead of hydrogen. What's crazy cool about all of our solutions is that pH and pOH of a solution will always add up to 14. So if the pH is equal to 7, because 7 plus 7 equals 14, the pOH would also be 7. If the pH is 3, what would be the pOH? Well, 3 plus what equals 14? That's going to be an 11. If the pH is 13, 13 plus what gives me 14? That's a pOH of 1. Do these ones on your own. Hopefully you decided that the pOH is 8 because 6 plus 8 is 14. And here the pOH is 14 because 0 plus 14 is 14. We're about to do some big math, my friends, so hold on tight. If the pH of a solution is 10 and I want to find the hydroxide concentration, then I need to kind of put my hydroxides and my hydrogen ions together. Remember that the negative log of the hydroxide ion concentration is going to be the pOH. So if I want to find the hydroxide concentration, I kind of have to go backwards from the pOH to figure out that concentration. To get the pOH, we found the exponent. To go backwards, we're just going to put it back in its exponent spot. But because I'm looking at hydroxide, I can't use my pH. I need to use my pOH. So my first step here, I need to find my pOH. If the pH is 10, Remember that pH plus pOH equals 14, so the pOH is going to be a 4. pOH is 4, pH is 10. This is my negative exponent on a 10 when I'm looking at the hydroxide concentration. So if the pOH is 4, that means that 4, when it's negative, is my exponent on a 10. This is my hydroxide concentration. Negative log of 10 to the minus 4 is 4. And so if the pOH is 4, then my hydroxide concentration is 10 to the minus 4. If you don't love 10 to the minus 4 molarity, you can rewrite it in standard notation, 3 zeros and a 1 molar. This is my concentration of hydroxide because the pH is 10. Good. Let's do one more together, and I'm going to have you do one on your own. The pOH is 2. What's the hydronium ion concentration? To find this, I need to use pH is equal to the negative log of the hydronium ion concentration. I need to figure out what that is. Right now, I only have the pOH. I can't use the pOH. I need to use the pH. If the pOH is 2, remember that pOH plus pH equal 14. If 2 is the pOH, then the pH is going to be 12 because 12 plus 2 equals 14. If the pH is 12, that means that this is the negative log of the hydronium ion concentration. To find a negative log, I figure out what's the exponent on a 10. Since 12 is my negative exponent on a 10, the hydronium ion concentration is going to be 10 to the negative 12 molar, or 0.11 zeros, that's 3, 4, 5, 6, 7, 8, 9, and a 1 molar. This is my concentration of hydronium ion in this solution that has a pOH of 2. Good. You do one. If the pH of a solution is 8, figure out first what's its pOH and then use that to find its hydroxide concentration. Remember that pH plus pOH equals 14. If the pH is 8, the pOH must be 6. The pOH is 6 if the pH is 8. To find the hydroxide concentration, I'm going to take the pOH and I'm going to put it as a negative exponent on a 10. So the hydroxide ion concentration is going to be equal to 10 to the negative pOH, and so it's going to be 10 to the minus 6 molar, or 0.5 zeros and a 1 molar. Moles per liter is the concentration of the hydroxide ion in this solution. Good. All right, we're going to take it one step further and not just look at molarity, but we're going to go all the way to grams. So let's say that I have 2.5 liters of acid that has a pH of 4, and I want to figure out how many grams of hydrogen chloride did I have to put into that solution to get that pH. So lots of steps. First up, if the pH is equal to 4, that means that the hydrogen ion concentration must be equal to 10 to the minus 4, because we know that pH is the negative exponent on a 10 when we're looking at that hydrogen ion concentration. So we're just going to put that pH back into its spot as an exponent on a 10, a negative exponent on a 10. So my hydrogen ion concentration is 0.3 zeros and a 1, 10 to the minus 4 molar is my hydrogen ion concentration. It's also my acid concentration. So I'm going to take 0.0001 molar. I know that that's equal to X moles over liters of solution. How many liters do I have? 2.5 liters. So I'm going back to my molarity formula. Remember that molarity equals moles over liter, moles of solute over liters of solution. I have 2.5 liters of solution. I'm going to plug that in for liters. Moles I don't know yet. I'm going to multiply both sides by that 2.5, and that's going to give me the solution for X. So X is going to be equal to 2.5 times 0.0001. That's equal to 0.00025 moles of hydrochloric acid, HCl, hydrogen chloride. this is not my final answer yet because I need not just moles, but grams. So I'm going to take my 0.00025 moles of hydrogen chloride and turn that into grams. I have moles on top, put moles on the bottom, put grams on the top so that my moles cancel out. I'm going to look at my handy dandy periodic table. Hydrogen is 1.008 and chlorine is 35.453. So the molar mass of hydrogen chloride is 36.461, the sum of those two guys. So with my handy dandy calculator, 0.00025 times 36.461 divided by 1, and I get a grand total of 0.0091 grams of, whoa, I missed my box, grams in that 2.5 liters of solution. Good. All right, I'm going to have you do one of these on your own, and then we're calling this lesson done, my friends. So, if we have 450 milliliters of a solution with a pH of 14, I want to know how many grams of sodium hydroxide are needed in that solution. First step is to figure out what's the pOH. If the pH is 14, what's the pOH? You're going to use that pOH to find the hydroxide concentration, which will be equal to the sodium hydroxide concentration. Use molarity equals moles over liter to find the moles of the sodium hydroxide, and then use molar mass to turn those moles into grams. Go. All right, so the pH is 14, and we know that pH plus pOH equals 14. The pOH must be 0. If the pOH is equal to 0, then the hydroxide concentration is 10 to the 0 power, or negative 0, but that's weird. We usually don't call 0 as positive or negative. That means that the concentration of the hydroxide ion is 1 molar, because 10 to the 0 power is 1. So if I have 1 molar sodium hydroxide concentration, that's equal to X moles over, oh my gosh, I have milliliters, not liters. We have to turn our 450 milliliters into liters. We do that by dividing by 1,000. 450 milliliters, there's 1,000 milliliters in 1 liter. 450 divided by 1,000 is 0.45 liters. 0.45 liters is what I'm putting into my molarity formula. Multiply both sides by 0.45 to solve for X. X is going to equal 1 times 0.45. That's 0.45 moles of sodium hydroxide. Turn those moles into grams. 0.45 moles of sodium hydroxide. We know that with moles on top, I want to put moles on the bottom, grams on the top. Sodium is 22.990. Oxygen is 15.999. Hydrogen is 1.008. That adds up to a grand total of 39.997. With my calculator, 0.45 moles times 39.997 grams per mole gives us 17.99865. So many digits. We're going to keep 1 sig fig. That 7 is going to turn that 1 into a 2. Just about 20 grams of sodium hydroxide is in my solution. You did it! We talked about characteristics of acids and bases. We talked about how acids dissociate into hydrogen ions and many bases dissociate into hydroxide ions. Water can dissociate into both of those things, which is crazy cool. We talked about some acid-base indicators. We'll play with those in lab. We defined logarithms. Logarithms are the maths of finding exponents. We calculated pH and pOH. Good work today.